After finally receiving the prototypes and after assembling the missing components, I switch on the board and nothing. After days of troubleshooting, I realized I made a fatal mistake in my design. If you're new to this video series, my name is Sarah, I'm a solo engineer, and a few months ago I started on this main quest to build a portable air quality monitor that consumers can use. Something small enough to clip to your bag and that can tell you the air quality around you at all times. So since then, we went from the idea being in my mind to designing the electronics, building up a website and starting to take pre-orders. And in the last episode, I finally got all the parts I needed to assemble the first prototype. So that was the exciting part coming up, testing the boards and seeing if everything worked as expected. So did it work? And the short answer is kind of. Some parts work in the end, but some others don't. So let me walk you through the circuit board design. Designing a circuit board has two steps. The first step is the schematic, and basically that's a drawing of what connects to what, which pin goes to which pin. And in the schematic you don't specify anything about the physical world. In my case, I think the schematic was pretty easy. Every integrated circuit I have on my board has a datasheet, so I followed the instructions on the datasheet. So it was a matter of putting things together and making sure to connect them correctly. The schematic is the foundation of the design, and you need to make sure the connections are right, otherwise the layout is also going to be wrong if the schematic is wrong. Before going to the layout, we need to specify which components we're using, like which sizes and form factors we're using. Every component needs a footprint, and many components are included in the main KiCad library, and the ones that were missing I downloaded from other online libraries. So this step is really important. You need to select the right footprints and the right component sizes. And finally we get to the layout, which is the step where you start placing things around. It might seem totally arbitrary, like there are infinite ways of doing this, but once you put together all the constraints that you have from the individual components, from your design specification, then you see that you have a lot less freedom than you think. Let's start from the microcontroller. It's a Bluetooth module, and the Bluetooth module has an antenna on it, so it needs to be placed on the side. It needs to be away from ground planes and other components that can interfere with the antenna. Then we have the PM sensor, the particulate matter sensor, and that uses infrared lasers. So it needs to be placed in a way that it can have, I think, 30 centimeters of unobstructed view, and it needs to be pointed outwards. It also produces a lot of heat, so it has a PCB heatsink, and in that area we cannot place other things. Then we have the CO2 sensor. It needs a way for the air to be in contact with it, and it's also sensitive to heat. So these two constraints made me put the CO2 sensor at the bottom and the PM sensor at the top. It means that the product will have sort of a main orientation, like it can't be flipped around for the sensors to work properly. Then the power management circuit has a layout that you need to replicate. Then we have a USB port for charging, and that one has to be on the side. And then we have some components that are like to interact with the users, like a button and two LEDs. Those also need to be placed in a way that makes sense for the enclosure design as well. And that's why we ended up with this layout. As I mentioned in the last episodes, I received all the parts while I was in Italy on vacation, so I did not have my equipment with me, but luckily my friend's dad has a company that does electronics as well, and I could borrow their lab and equipment. So to test prototypes of a new design, it's not advised to just plug it into the USB and see if it works. It's good to follow a step-by-step approach, testing progressively if all the single parts of the board work. So the first thing I did was to solder some wires and feed the 3.3 volts to the board to see if the microcontroller would turn up, and it did. I tried flashing a basic blinky software to make the LED blink, and that was nice. But after that I got too optimistic and a bit impatient, and I soldered on the power management circuit and also the CO2 sensor. And then when I went to plug in the USB this time, so to be able to convert the 5 volt into 3.3, it didn't work. I was able to measure only 0.8 volts on the rails where there should have been 3.3. And 0.8 volts is not great, because if it was 0, then I could say, okay, something is not connected. 0.8 makes me think more like there is something pulling it down, there is some conflict somewhere. So I spent the next hours and days trying to figure out where the issue is. And keep in mind that I assembled the components using a hot air gun, so I wasn't confident in my soldering. So I did not know if it was the design to blame or the soldering. So yeah, that was pretty disappointing. My holiday ended and I had to fly back home to Sweden with a not working board, which was not a nice feeling. So yeah, at this point I pretty much realized that I need to be able to work with SMD components, so the surface mounted components, and I did not have equipment at home to do this. So I spent 300 euros and ordered a few things. The most exciting thing that I ordered was a hot plate, which I have here. It's like 5 by 5 centimeters, so my board is slightly bigger, but it works pretty well. And luckily my board is one-sided, so it's perfect for the kind of use case. The issue that I found with the hot air station is that it's very hard to control the temperature, and you need to preheat the board, and you can blow away the small components that are next to the one you're trying to solder. Okay, so with the new equipment, I restarted the troubleshooting process for the prototypes. I went one component at a time. So I managed to replicate the issue that I found in Italy. And after measuring a bit on and off, I decided to retry reflowing a board. Reflowing is basically making the board go through the same temperature cycle that it would in the manufacturing process to assemble SMD component. Magically, the 3.3 volt rail was working, and I could finally power the board via USB-C and flash software and test things. So yeah, I probably had bad soldering somewhere on the first board that I tried. So I took the chance to test the Bluetooth, if the Bluetooth communication worked, and it did. I tested the LEDs on the board, which also worked first try. Then I tested if the battery worked, powering the board from the battery without the USB. And then I went on to add a new component. Like I tried resoldering the CO2 sensor. And after that I saw the same problem with the 3.3 volt rail being at 0.8. And I spent, I think, a day troubleshooting this. I was convinced maybe the sensor was broken. It has like internally a short circuit or something. But when I went back to the power management chip datasheet, then I saw that it has startup current limitation. And in my design, the CO2 sensor is enabled by default. Whenever I would plug the USB, sensor would draw too much current and the power management circuit would go into this self-protection mode. Luckily, I could fix this by just removing a resistor from my design. So this was fixed quite easily after I realized where the problem is. So finally, I could see some CO2 readings, temperature and humidity readings as well, which was pretty nice because that means that my air quality monitor is halfway there. The last part to make it a full air quality monitor, or at least for my intended design, was the particulate matter sensor. So I went on, added the connector, plugged in the sensor, and it didn't work. And this one is a bit tricky because it uses SPI. It's a bit hard sometimes to get it to work, especially with the Zephyr, which is operating system, like the firmware operating system I'm using. All the Nordic semiconductor chips use this. Software-wise, I didn't find any issues. I didn't manage to get any indication of the sensor being alive. So then I went back to the sensor datasheet, and this is the moment where I realized my design mistake. Basically, the sensor, which is a little flex PCB, has the reversed pin numbering compared to the connector. So my design on the connector is mirrored to what it should be. So yeah, this was definitely a mistake on my end. It's also not intuitive from the perspective of those who designed the sensor, because I did not see or think that the sensor could have a different pinout than the connector. So yeah, that also means that the two sensors that I used to test have received some weird combination of power and they are probably broken. So that's the most expensive part. Yeah, and unfortunately this is not something I can fix with the soldering iron or with the hot plate. It's not about desoldering something or adding some wires. I need to redesign my board. We go from revision A to revision B. To be fair, revision A is not that horrible. I managed to verify a lot of the functionalities of the board and I've seen that they work, so this is actually pretty good for being the first try. I also figured out that the CO2 sensor needs to be disabled by default, and when the CO2 sensor is disabled, the I2C, the bus, the communication that is used to communicate with it, goes down, and I need to make sure that I can disconnect it. With the CO2 sensor working and the Bluetooth working, I'm able to start testing the end product in a way. So I made a dashboard on my computer and I connected the prototype board via Bluetooth to my computer, and I can see these CO2 readings in real time. So this unit here is functional and has been running on my desk for, I think it's about a week now. So I managed to fix some firmware issues and make sure that the Bluetooth protocol implementation is good. The next step for that would be to make the mobile app. The other good thing that I saw is that the battery doesn't discharge as much as I thought it would. I mean, of course, one of the most power-hungry components is not in place yet, but I haven't implemented any sleep mode or power optimization, and I'm reading the CO2 sensor every minute, and the Bluetooth is also on all the time. So I think we might achieve those 6-7 days of charge with the battery. So after realizing my mistakes, I did not waste any time and went straight into designing the revision B. And that more or less adds like 2 weeks on the timeline for this project. But I already got the new PCB for revision B actually. It's right here. And I'm waiting for the components, the parts that go on it, which are gonna arrive in the next couple days. So hopefully I'm gonna be able to get it up and running pretty quickly this time. Let's talk about lessons learned from this first prototyping run. Multiple revisions are pretty normal. It's very rare that you would get a design right the first time. Of course, if you're an experienced hardware designer, then there are less chances of something going wrong, but in this case, like, this is the second ever PCB I designed, so I accept making a mistake. But the issue is that it took me almost 2 months to get the first prototype in my hands and be able to test it, and that's too long. The most frustrating part was coordinating all the packages and all the deliveries. And also, I thought that I would save time by asking the PCB manufacturer to assemble the boards, or at least partially assemble them, but that actually was not a good idea, because now I have 5 boards with some components, some of them very expensive, that I basically cannot reuse. So next time I'm gonna assemble myself one board to see if the design works, and if that works, then I'm gonna assemble more. So yeah, I got a bit frustrated with the waiting time, but that's how it is when you work with the hardware design. The other thing that I want to do, that I already did in the revision B design, is to add extra LEDs to see that the power rails are working, because sure, you can test that with a multimeter, but it's much easier to see it with an LED. The main reason why I didn't have this in revision A was I was concerned about space and cost, but there is enough space to add 3 LEDs, and for cost I will just remove them so they're not placed when I order the production run. Alright, so what's next? I have to admit I've been procrastinating the mechanical design. I think it's a bit overwhelming, because there are many options of how the enclosure will look, and there is this big unknown of how to make it splash-proof, because this needs to be carried outside, and outside it rains. And then there is also the aspect of how to make it look nice, because this is a consumer product. The engineering brain wants to make it minimal, easy to manufacture, with the minimum amount of parts, but I cannot ignore that the aspect of it is important. So I want it to look nice, and I want it to look cute, and something that people actually want to carry around. So if you have any creative ideas or inspirations for the enclosure design, comment down below. I read all the comments. Now I have this month for finalizing the enclosure design. I've started 3D printing some things. Yeah, they're still very unrefined. From the marketing and sales department, I can see that my website is getting more and more visits. This last 28 days, it got like more than 200 page views, which is not crazy, but it's still good and growing. And then I got 3 more pre-orders since last time. So the spots for this first batch are slowly but steadily getting filled. So now it's time to go get some stuff done. I'm Sarah, this is Busy Wait. See you in the next.